of chemistry that is concerned with the speeds or rates of reactions is called chemical kinetics. Chemical kinetics is a subject of broad importance. It relates, for example, to how quickly a medicine is able to work, to whether the formation and depletion of ozone in the upper atmosphere are in balance, and to industrial problems such as the development of catalysts to synthesize new materials. Our goal in this chapter is not only to understand how to determine the rates at which reactions occur, but also to consider the factors that controls these rates. By the end of this model, you should be able to list the factors that affect the rate of chemical reaction. Determine the rate of a reaction given time and concentration. Relate the rate of formation of products and the rate of disappearance of reactants given the balanced chemical equation for the reaction. Also, you must explain the form and meaning of a rate law, including the ideas of reaction order and rate constant. You will be able to determine the rate law and rate constant for a reaction from a series of experiments given the measured rates for various concentration of reactants. Also, you will be able to apply the integrated form of a rate law to determine the concentration of a reactant at a given time, and you may apply the relationship between the rate constant of a first order reaction and its half-life. So, chemical kinetics is basically the study of rate at which a chemical reaction process occurs. Besides information about the speed at which reaction occur, kinetics also sheds light on the reaction mechanism. So it also helps us to understand how the reaction occurs at a molecular level view of the path from reactants to products. There are several factors that affect the reaction rates. The first one is the physical state of a reactant. Also, the reactant concentration may affect the reaction rate, the reaction temperature, and the presence of a catalyst. Basically, these are the four factors that may affect a reaction rate. Let's describe each of them. So, the physical state of the reactant. The more readily the reactants collide, the more rapidly they react. Homogeneous reactions are often faster. So it's really important to understand that as higher the collision, higher the probability to have a reaction. Okay, so if somehow you can increase that collision between the molecules, you also increase the probability that both molecules can react and you have a product. Heterogeneous reactions that involve solids are faster if the surface area is increased. So in this case, for example, a fine powder reacts faster than a pellet or a tablet. So that's why you need to those if you have, for example, some piece of solid, it will be easy if you powder them. So that you increase that surface area and you increase more the probability of the collision between those molecules to have a possible product. Also, the reactant concentration. Increased reactant concentration generally increase reaction rate. Why? Because since there you have more molecules, you could have more collisions. If you have more collision, you increase the probability of the reaction. So here we have example of a steel tool heated in air. We have a 20% of oxygen, and we can see here the reaction. It glows. But if you have a 100% of oxygen, then the reaction is more vigorously, is more intense. Okay, so the reactant concentration also could affect the reaction rate. The third one is a temperature. The reaction rate generally increase with increased temperature. What do you think? Why the temperature could affect the reaction rate? Because the temperature increase also the kinetic energy of the molecules, and if you increase the kinetic energy, those molecules are going to move faster and could collide, find another one and collide, and then you can have maybe a reaction there. So the kinetic energy of molecule is related to the temperature. At higher temperatures, molecules move more quickly, increasing the numbers of collision and the energy the molecule possessed during the collisions. And the fourth is the presence of a catalyst. The catalysts affect the rate without being in the overall balance equation. So a catalyst is a molecule or a surface that is not part of the chemical reaction but help to increase the rate of that chemical reaction, but it doesn't take part of the reaction. The catalysts affect the kinds of collisions, changing the mechanism. Individual reactions that are part of the pathway from reactant to products, and we're going to see this a little bit later. And the catalysts are critical in many biological reactions. We have a lot of catalytic process in our body that they need this type of catalyst so that reaction could take place inside our bodies. Let's talk about the reaction rate. The rate is a change in concentration over a time period. Let's explain some of the symbols in this equation. The triangle means change in. Also, it's called delta. Okay, so the delta is the name of this triangle that means change in. This symbol represents the molar concentration, so that's why this part is the change in concentration. And the T represents time, so this is the delta T, or change in time. In other words, the rate is equal to the change in concentration divided by the change in time. There are different types of rate measured. The first one is called the average rate. The other one is instantaneous rate. And finally, the initial rate. And we're going to discuss this in the following slides. But first, let's follow a reaction. We have this type of reaction, C4H9Cl plus water, producing C4H9OH plus HCl. Remember that at the left side of this arrow, they are the reactants. At the right side, we have the products. So these two reactants combine and produce these two products. So here we have a table that shows at different times the concentration of C4H9Cl, the concentration of the reactant, and they measure the average rate between these two times. In each one, you can see that they are averaging the rate, doing the average of the rate between two times. So the rate of a reaction is measured using the concentration of a reactant or a product over time. So you can measure how the reactant has been consumed, or how do you have or how the product has been formed. So you can use any of those to measure the rate of a reaction, okay? Following how the reactant has been consumed or following how the product is formed. And this is over time. In this example, C4H9Cl, we're following the reactant, how the reactant is consumed. That's why you can see here that the concentration is decreasing, okay? Because this is the reactant, and the reactant is consumed during the time, okay? So let's plot the rate data. A plot of the data gives more information about rate. Through this graphic, we're gonna find a different type of information and very valuable information. These figures show instantaneous and initial rate of the earlier example. So this is basically how the behavior of that reaction. Okay, this is the concentration of C4H9Cl, the concentration of the reactant versus time, and as you can see, the concentration is decreasing because we're using here the reactant, and by time the concentration is basically consumed, is reducing. So the slope of the curve at one point in time gives the instantaneous rate. So at any point, specific any point, if you can measure the slope at that point, that will be the instantaneous rate. The instantaneous rate at the time zero, it's called the initial rate. So if you can measure the slope here at point zero, this one is called the initial rate. This is often the rate of interest to chemists. Let's talk about the relative rates. As was said, rates are followed using a reactant or a product. Does this give the same rate for each reactant and product? The rate is dependent on stoichiometry. If we follow use of C4H9Cl and compare it to the production of C4H9OH, the values would be the same. Now, note that the change would have opposite signs. One goes down in value while the other goes up. So here we have the rate. The rate relative to the C4H9Cl is minus the change in concentration over the change in time. Remember that rate is change of concentration divided by change in time. In this case, this is the reactant. So this is the change in C4H9Cl divided by the change in time. Now we need to add this minus sign here. Why? Why do you think we need to add this minus sign here? Because change usually is the final concentration minus the initial concentration. Final concentration minus initial concentration. So that means that this is going to be the final concentration is lower than the initial concentration because the reactant is consumed during time. So the final concentration is going to be less than the initial concentration. So that is good. That subtraction is going to be negative. So you need to add here a negative because the rate needs to be positive. So this negative that is going to have here multiplied by this negative is going to be positive. With the product, you don't have that problem because the final concentration of the product is going to be always higher than the initial concentration because during time you're producing more product. So at the end, when you subtract the final concentration of products minus the initial concentration is going to be positive. So that's why the rate for all the products is going to be positive, or you don't need the negative sign here. So for the reactant, you need to place a minus here. For the products, you don't need to place any sign in front of it. So what happens if the equation is not 1 as the one that we saw before? What will the relative rates be for the following reaction? 2O3 in gas producing 3O2 also in gas. Here we have one reactant, that is the O3, ozone, producing 3 molecules of oxygen, O2. So we have now the stoichiometry is 2 of the reactant produce 3 of the product. So how will be the relative rates for this reaction? So O3 is the reactant, so this we need to add a minus here. And because we have 2 moles of O3, that will be 1 over 2. So this is the relative rate for O3. And for oxygen, O2 is going to be the change in concentration of O2 divided by the change in time. And because we have 3 moles of product, it will be 1/3. And that will be the expression of the relative rate for O2. So these two rates are going to be equal. Okay, these two rates now are going to be equal. So the rate is going to be equal to minus 1/2 of the change in concentration of O3 divided by time. And also the rate is going to be equal to 1/3 the change in concentration of O2 over the change in time. So how can we determine the effect of the concentration on the rate of a reaction? Well, we keep every concentration constant of any of the reactants except for one reactant, and we see what happened to the rate. Then we change a different reactant. We do this until we have seen how each reactant has affected the rate. So if we have 2 or 3 different reactants, we keep two of them at a constant concentration while we change the concentration of the other one. And we see what happens to the rate. We compare like the two different concentrations and what happens to that um, rate of reaction. So let's see an example so that maybe helps in this concept. Here we have NH4 plus NO2 minus, and this will produce nitrogen gas and 2 molecules of water. Here we have two reactants. We have NH4 and NO2. So what we're going to do is we're going to keep one of maybe NH4 first, constant, and we're going to change the concentration of NO2. And then we're going to measure the rate of this reaction. When we have that, those results, then we're going to keep NO2 constant and we're going to change NH4, and we're going to evaluate what happened with the rate when we change the concentration of NH4. So here's a table of the rate data. In the first three experiments, we can see here that we changed the concentration of NH4 and the concentration of NO2 was constant. So if we see any difference in the rate, that this difference will be due to the concentration of NH4, the effect of NH4. In experiments from 4 to 6, we can see here that we have the NH4 constant in all three experiments, and in experiments 4 to 6, in these three, we have three different concentration of NO2. So if we see some difference in the rate, it's going to be due to the change of concentration of NO2. So these are 6 different experiments. Experiment 1 done by these two concentration, and when we add both concentration, we measure the initial rate. For the second experiment, these two concentration, we measure the initial rate, and so on for the other 6 experiments. So as I told you, from 1 to 3, we're going to see the effect of NH4 on the rate, and from 4 to 6, we're going to see the effect of NO2 on the rate of the reaction. Okay, so that's how we can determine the effect of the change of concentration on the rate of the reaction. So the result of this is the rate law. The rate law shows us the relationship between the rate and the concentration for all the reactants. And this is the expression for rate law. The rate is going to be equal to K times the concentration of NH4 plus times the concentration of NO2. In this case, we have that the rate is going to depend on both concentration. Now, let's see this. If we evaluate, for example, the experiment 1 and experiment 2, we can see here that we duplicate the concentration of NH4. And when we see the rate also was duplicated. Okay, so that means that when the effect is the same, the order of the reaction but for that reactant is the first order. That's why this is a 1 here, but we never wrote the 1, but this is first order with respect to NH4. And what is the order for NO2? We can choose experiment 4 and experiment 5, and we can see here that we also duplicate the concentration of NO2. And when we observe the rate from experiment 4 and 6, we also see that the rate was duplicated. So that means that also for NO2, the order of reaction for NO2 is also first order. So the exponents tell the order of the reaction with respect to each reactant. In this example, as I mentioned before, the order with respect to each reactant is 1. Okay, it's first order with respect to NH4, and it's first order also with respect to NO2. And the order of the reaction is second order, okay, because we just add up all the orders of the reactants. So with respect to each reactant, this one is first order, this one is first order, but with respect to the whole reaction, is going to be second order because this and this would add 1 plus 1 and we have a 2 that is a second order. So what is K? K is the rate constant. It is a temperature dependent quantity. Okay, so the K Here in the rate, this is a constant, and we're gonna see in the following slides how can we determine or calculate the rate constant. So the first order reaction. Some rates depend only on one reactant to the first power. These are first order reactions. Now we're talking about a reaction that is first order, so this involves just one reactant that is first power. And the rate law becomes rate is equal to K times the concentration of A. This is a hypothetical reactant, and this is power of 1. Okay, so here we have the expression of the rate law for a first order reaction. Rates equal to the K, the constant, times the concentration of the reactant elevated to the power of 1. So let's see how can we find a relation between the K and the concentration of A. To do this, we're gonna do an integration of this this formula or this expression of rate. We know that rate is equal to K times the concentration of A. But also we learned that rate is equal to minus the concentration of the change concentration of A over the change in time. Remember that A is a reactant, so that's why we have here a negative, okay? So this is the expression of rate, this is the expression of rate, so that means that this value and this expression, they are what? They are equal, okay? So we have that K times the concentration of A is equal to minus change in concentration over change in time. Now we can rearrange this equation. Okay, so don't worry so much for the math or the rearrange. You must need to understand the concept that we're going to discuss in a few seconds. And then we do an integration using the natural logarithm of this expression. And at the end, we're going to have something like this. The natural logarithm of the concentration of A is equal to minus K times time plus the natural logarithm of the initial concentration of A. This is the expression of the first order reaction. It's interesting because this expression is similar to the equation of a line. This will be y, this will be mx, and this will be b. Y is equal to mx plus b. The reason that we induce or create all this or went through all this integration for this equation is because we can express this in a straight line, and it's easy to work with a line than with a curve. Okay, and we're gonna see this basically in the following example. Here we have methyl isonitrile, and this one is converted to acetonitrile. So this is a first order reaction. Rate is equal to K for the concentration of the reactant, that is the methyl isonitrile. And without doing all those integration that we did before, the curve that we have or the graphic is like a curve. But if we create those integration, then we have a straight line, and it's more easy to work with a straight line than with a curve, okay, to obtain the different values. So that's why we went through all those integration and all those math. But at the end, the most important thing is the expression that we have for the first order reaction. So how can we find the rate constant? Besides using the rate law, we can find the rate constant from the plot of the natural logarithm of A versus T. So we have this. The natural logarithm of the concentration of A is equal to minus KT plus the natural logarithm of the initial concentration of A. And as I mentioned before, this is equal to the expression of a line. So in the y-axis, we're going to have the natural logarithm of the concentration of A, and m is going to be equal to minus k. So the slope of this line is going to be equal to the rate constant. So we can obtain the rate constant directly from the graph by measuring the slope. Okay, the x-axis will be time, and the intercept will be basically the natural logarithm of the initial concentration of A. So the plot will give a line and its slope will be equal to minus k. The concept of half-life plays a key role in the administration of drugs into the body, especially in the elimination phase, where half-life is used to determine how quickly a drug decreases in the target after it has been absorbed, or also how can that drug be affected by the elimination rate of the system. So, the definition of half life is the amount of time that it takes for one half of a reactant to be used up in a chemical reaction. So, the half life is the time that you need so you can be in the half of the amount that you have as compared at the initial point. So, here we have a graphic. Um, Here we have the pressure is basically associated with the concentration. So 150 torr, half of 150 torr is 75. So here, when we reach the 75 torr, we look for the time, and that will be the half-life for CH3 and C. 75, half of 75 is 37.5. So when we reach 37.5, we can look for that time, and that will also be the half-life. So all half-life basically are the same for the same species. In a first order reaction, as we have seen in the last couple of slides, we have that. So here we have the natural logarithm of the concentration at any time is going to be equal to minus kT plus the natural logarithm of the initial concentration. If we are now working to determine the half-life, that means that we are looking for the time where the initial concentration is going to be half. So at this time, this concentration is going to be half of the initial, because we're talking about the time when we can reach half of the concentration that we have as compared to the initial one. And now we can do some rearrangement, and at the end we're going to have this expression. So the half-life for a first order reaction is going to be equal to 0.693 divided by the rate constant. That means that the half-life is gonna be related with the rate constant. If my rate constant is small, then the half-life is going to be large. If my rate constant is large, then my half-life is going to be small. So the relationship between the half-life is going to depend specifically for the first order reaction. The half-life is going to depend just only on the rate constant, okay, for the first order reaction. Let's talk about the second order reaction. In the second order reaction, we're going to find some rates that depends only on a reactant to the second power. Or also maybe we can have two reactants, but each of them is going to be first order. And as we mentioned before, when we add both, it's going to be a second order reaction. Okay, so the second order reaction is not just of one reactant as a second power. We also can have two reactants, and each one is going to be in power of one. So that makes the total reaction a second order reaction. These are second order reaction. The rate law becomes something like this. This is basically the simple expression when we just have one reactant, okay, that is involved in the rate. So rate is going to be equal to the rate constant times the concentration power of 2. This makes the whole reaction a second order reaction. So as the same as we did before with the first order reaction, this is basically the definition of the rate for the second order reaction, K, the constant, rate constant, times the concentration, the power of 2, and this is the other definition that we know. So when we combine both, we have something like this, and then we rearrange them as we did for the first order, and using calculus, we obtain this type of equation. Okay, and this one is also an expression similar to the first order in the sense that we have also here an expression of a line. Okay, we have here the expression of a line, but In this one, we have basically the inverse of the concentration, while in the first order reaction, we have the natural logarithm. So those are the difference between these two expressions. For the first order, we use the natural logarithm. For the second order, we use the inverse of the concentrations. So for using an example of a second order reaction is the decomposition of NO2. And we can see here that if we just plot the values of time versus the natural logarithm of O2, we don't have that expression of a line, we have a curve. But if we use the inverse, then here we have the line, okay? And as the same way, also the slope is going to be also the constant rate for this second order reaction. The half-life and second order reactions, basically we're using this this expression for the second order reaction. After some derivations and math process, we finally obtain this equation. That is the half-life equation is going to be equal to 1 over K times the initial concentration of A. Okay, so this is the expression for half-life to a second order reaction. This is the most important equation that we need to understand and learn. And this one, as different from the first order reaction where the half-life depends on the rate constant, in this one, the half-life is going to depend also on the concentration of the reactant and the initial concentrations. That's going to be a really important difference of the half-life from the second order to the first order.